morning. I'm really excited to introduce Dr. Tom McAndrew, who is an assistant professor at Lehigh University College of Health. His research focuses on the forecasting of infectious diseases, and he studies how best to ensemble forecasting models, how to assemble expert prediction of future disease trends, and how to crowdsource forecast predictions from the public. He's also an expert on clinical trial design from his time as Associate Director of Biostatistics at the Cardiovascular Research Foundation. During the COVID-19 pandemic, he's carried out really interesting work to use expert and general crowdsourcing to predict not only COVID-19 trends, but also the timing and efficacy of vaccine trial results. And today, I think he'll be talking about methods to combine computational model projections alongside human judgment. So please take it away.
Thanks for the intro, Spencer. A lot of folks don't mention my my time in industry in the trials world. I had to wear a tie, so I'm trying to forget it. Let me share my screen, and can you just tell me if you can see the presentation here?
Yep, we can see it.
Okay, cool. Let me see if I click play. You can probably see the other one, right? So I'm gonna switch it.
No, we were seeing the right one initially.
You were seeing the right one? All right, let me switch it.
Yeah.
Let me switch it again. Right one now?
Yep.
All right,
that's
cool.
Perfect.
So I wanted to talk about, I wanted to kind of random walk through some of the research I've done, combining probabilistic predictions from computation models and from people. I've enjoyed asking people questions for a long time now, since my PhD, and thought, maybe this can work for predicting the trajectory of infectious diseases also. So here's the idea. There is some probabilistic information about the future, and you can think of it as this blue sphere that is all possible information about the future. And if you knew everything in that blue sphere, you would be able to predict the future perfectly. And computational models in green here have a certain piece of that pie. And you could think of a computational model as mapping this probabilistic information that we have about the future onto some projections. So in the right here is time on the horizontal axis, and the top panel is number of confirmed flu hospitalizations, on the bottom is number of confirmed COVID hospitalizations, and a probabilistic prediction for the state of Pennsylvania, which is FIPS 42, from a computational model. And so it maps structured, objective data into the future. And that's great. But humans, humans have access to that type of data too, but we also have access to other sorts of data. We have access to subjective information, past experience, and intuition. And computational models do not necessarily have access to that type of data. And so if you were able to ask experts and train forecasters to make predictions about the future, they will make different predictions because they have different information than a computational model has access to. And maybe we should combine those together, and maybe the hypothesis is that maybe that would result in a more accurate forecast of the future. That's my idea pitch. Before I start talking about the chimeric forecasting work, I wanted to talk about two previous projects to show you that I do know a little bit about what I'm talking about, very small amount. The first one was an expert judgment project. We launched 13 surveys. We started them February 18th, 2020, and they ended May 11th, 2020. We enrolled 44 experts in the modeling of infectious disease, and we asked them questions about this new thing in February 18th called COVID. And to give you a sense of what the world was like February 18th, 2020, I believe the first question we asked is, do you think there will be 5 cases in the United States 2 weeks from now? And so it was a different place back then. And to give you an example of some of the questions we asked and the results from that first project, we asked folks to predict confirmed COVID-19 cases. So on the left here in this panel, on the top is the dates we issued surveys to experts on the horizontal axis. On the vertical is predicted number of cumulative deaths by the end of 2020. The blue dark dots are the median prediction from all these experts and a 5th and 95th percentile. The black dashed line is the true number of cumulative deaths at the end of 2020. The bottom panel is the date the forecast was made for each of these surveys. And again, the truth is the black dot, the median's a blue dot, 5th and 95th percentile. Looking at the top plot, you know, experts gave a pretty early signal that the pandemic might be bad. Let's just put it that way, right? That it might result in a large number of cumulative deaths by the end of 2020. That said, there was large uncertainty here. You can see in that first survey, 316, folks said, well, it might be something like 250,000 cumulative deaths, but it could be anywhere from 5,000 to over 1 million. So they really weren't sure. Same story with cases. You know, in the beginning surveys, predictions were mostly optimistic. Experts tended to predict a lower number of cases than what was reported, and they learned over time and made better predictions. We also asked them about the total number of SARS-CoV-2 infections, not the reported ones, the true total, which we'll never really know. So on this panel on the right is again the dates on the horizontal axis, the predicted SARS-CoV-2. Green are the human expectations, blue dots median, 95th percentile. In yellow and purple are prospective computational models that tried to estimate this. There was one from Lover McAndrew from UMass Amherst, Perkins et al., Bedford, who made a paper about this, and Lou et al. And gray are also retrospective predictive, more computational models about what they think the number of US COVID infections were at that time. And human judgment seemed like roughly these. We also asked counterfactual questions for 3 different states. One of them is Texas. We asked about Georgia, Texas, and Washington in early May, late April. And we said in a few weeks, if the state reopened or if it didn't reopen, what do you expect the 7-day average of cases will be? And the blue is what actually happened, the predictions for what actually happened. So in Georgia, if restrictions were loosened at that time. In Texas, they were. And a full accelerated read did not happen. And we saw experts did pretty good at estimating the 7-day moving average, given what actually we were sort of by this project. And other folks were inspired by it too. And this group called Metaculus just to do another project.
Tom, we're I think you're breaking up a little bit. Is that, or is that just me? Is that my internet?
It could be mine.
It's me too.
Did you hear my counterfactual conversation? Should I read counterfactual?
I think I missed the conclusion of this slide.
Yeah. So 3 states, you know, experts were pretty good at predicting 7-day moving average of cases for these 3 different states under a restriction loosening or restriction not loosening scenario, and they were pretty good at predicting what actual I guess to be honest with you, I didn't expect them to do that, but they surprised me. They're surprising. Those are shocking, and inspired another project about the safety, timing, and efficacy of vaccine. We launched 4 surveys, June 18th, 2020, well before vaccines were August 30th, 2020. We enrolled 10 experts and 11 we call trained forecasters who are on this platform called Metaculus. And we asked them questions about efficacy. For example, when will the COVID-19 vaccine show greater than 7% efficacy? We asked about efficacy for a specific trial, the Oxford AstraZeneca trial about the ChAdOx vaccine. What will the efficacy of that be? We asked about efficacy by platform. We asked about efficacy by approval, either a normal approval process or a sped up or emergency authorization process. And the results were not nearly as good here. Folks did not think the approved vaccine would be as efficacious as it was. They expected under a normal process in this bottom panel in D, efficacy would be something like 70%. If it was rushed, it would be something like 50%. And it was quite a bit better than that, right? 95% or a bit better even. So they missed that target. They did. That said, the timing was, they were uncertain about timing of when a COVID vaccine would show efficacy. This is panel A. The truth was somewhere at the end of 2020, but they expected it to be 2021. right? So I think that humans in general, experts and trained forecasters in general, were surprised by the high efficacy and the speed. And I think that, I mean, that was certainly true of me. I didn't expect that to happen either, right? We also asked about safety, when a COVID therapy would show a survival benefit, and survival benefits by different platforms. Again, they thought that would happen later than when it actually did happen. We asked about specifically timing of approval, and we asked it in 3 different ways across multiple surveys. We asked when a SARS-CoV-2 vaccine would be approved in the US or the EU. Just when, tell me when. We asked when a SARS-CoV-2 vaccine would be approved in the US or EU for a standard or normal approval process and an emergency authorization. And finally, we asked just for the US, when do you think? In September, we asked, when will a SARS-CoV-2 vaccine candidate be approved in the US for a standard or normal process and emergency authorization? And in all cases, they thought it was later than when it would happen, but in that September survey, the median prediction was January 2021, not too far off from when it actually was approved. And so the kind of conclusions from this project is that, you know, humans might be good at predicting certain targets or certain questions and not so good at others. I guess we have a good sense of time. Okay, on to this third project. So those are the 2 previous projects. On to this third project of Chimeric.
One question on that. How much do you think the efficacy and timing are because of the kind of just unfamiliarity with mRNA vaccines, because that was just a completely novel thing, and maybe that, I guess, how much do you think is that versus just difficulty in predicting in general?
You bring up a good point. I mean, humans are influenced by certainly the unfamiliarity with what they're predicting, which this was a totally new space, right? The vaccine realm was really new for the trained forecasters, and even these experts didn't really, I don't suspect, know a ton about this new vaccine that was coming out in mRNA. Not only that, there was all sorts of subjective data that probably could have biased them in either direction. And there was some chatting between forecasters on this platform about different political things that were happening, right? Different things in the environment that I for sure suspect biased their predictions.
So a follow-on question, which I feel like I should have asked initially, what does it mean to be a trained forecaster? How does one become a trained forecaster? I'm thinking of those, I remember there was some book I read with some story about people who are really good at predicting if there's going to be an Iraq war or something like that. But I just don't know what, Could you describe what that is?
So for this one, we defined, I know that book too. It's called Super Forecasting, I think, or something like this. We defined a trained forecaster as someone who had to have been on this prediction platform called Metaculus. They had to have been making predictions actively for at least 1 year, and they had to have been within the top 1% most accurate forecasters on the website. So they had to be pretty good. They didn't know what they were doing. And then we posed this survey to them, and 10 of them agreed to it, and I think 30 didn't want to participate.
Okay, so this is a platform for crowdsourcing forecasts. I think I've looked at the website that you shared with, but so that's a platform that you can just crowdsource forecasts, and these are the cream of the crop.
These are the best ones. These are the good ones, or at least the questions that were asked on the Metaculus platform are not necessarily infectious disease. In fact, they're economic, political, all sorts of questions, right? And so they were the best at predicting a wide variety of targets, not specifically vaccines.
Thanks.
Yeah, and I'll give you a demo of the Metaculus platform at the very end because we're launching another survey. Why not? So project 3 was again, similar in style. We're posing questions to a crowd, but in this case, there's 2 different crowds. There's one crowd called Metaculus. These are forecasters from all over the world who sign up and are genuinely interested in forecasting. There are certainly people like that. Also, good judgment, in particular, the Good Judgment Open platform. It's open, meaning open to all folks who want to make forecasts. You yourself can sign up for Metaculus and Good Judgment and make predictions. There's no requirements there. We also looked at predictions from the COVID-19 Forecast Hub for this project. So we wanted to combine predictions from people and predictions from models with the hopes that it would lead to a more accurate forecast. We posed 6 surveys from January to June. The interval of time we let people make predictions was roughly 2 weeks. So it would be like January 1 to January 14th, 15th. That said, we cut predictions when we were going to combine them with computational models at the same deadline that the COVID-19 Forecast Hub enforced. So we let people make predictions, say, from January 1 to January 15th, but if the COVID-19 Forecast Hub's deadline was the 7th, we cut predictions at the 7th for this chimeric forecasting project. These surveys, we built summary reports for them too. That's why we let them kind of go longer than that. This first panel up here is the 6 different surveys. The survey open and close is in blue. The red is the forecast horizon, like the date we asked about incident cases and incident deaths. These are the only 2 targets we're asking about for this specific combination project. The black line is the COVID Hub model submission deadline, the vertical dashed line, and then this time series is the incident cases per week when we were asking. How you ask questions on Metaculus in this prediction platform and how you ask it in Good Judgment are different. For Metaculus, you can ask what will be the total number of new incident deaths due to COVID-19 in the US between these 2 dates, and they will provide, shown in this video here, a probabilistic prediction, which is a combination of 5 logistic distributions that you can shift and scale and weight to build your prediction, which I think is just awesome. It just seems, pretty cool, right? Good Judgment Open takes a different approach. They have a variable number of bins, so they might ask fewer than 14,000, between 14 and 16,000, between 16 and 18,000. You assign probabilities to those bins for what you think the truth will be. The 2 questions that are posed were, what will be the total number of new incident deaths due to COVID-19 between these 2 dates, and the total number of incident cases. We took those predictive densities from individuals, and we mapped them onto the COVID-19 Hubs quantile format. So for predictions of incident cases on the left and incident deaths on the right, we transformed those predictions into 7 quantiles, the same as the COVID-19 Forecast Hub for cases, and 23 quantiles for death. We wanted to make it as similar as possible. In gold here is the COVID Hub. In blue is Metaculus. In red is Good Judgment. So it's just an illustration for incident cases between February 21 and February 27, and deaths 21-27 on the right. And just a quick peek at the results. For surveys 1, 2, 3, 4, 5, 6, what I've plotted here is the median is a black dot, 25th, 75th percentile, 5th and 95th percentile for incident cases on the left, incident deaths on the right. The dashed black line is the truth, and the same color scheme for Good Judgment, Metaculus, and COVID Hub. And so my expectations was that computational models were going to blow human judgment out of the water, and that was not the case. And we're going to go into more details about this sort of summary result. That was my expectation was comp models are better. And as almost every day, I'm proven wrong about something, and it was that time. So let's talk about. I should say, we didn't ask only about cases and deaths for these surveys. We asked 7 or 8 questions every single survey, just to give you a quick idea about what the questions we asked were. We asked about adult, pediatric, and previous day admissions to the hospital. We asked about deaths and positive cases. We asked about cumulative number of people who have received 1 or more doses of a COVID vaccine. We also asked about the cumulative number of people who would be fully vaxxed. We also asked questions about variants of concern, like how many variants of concern do you think there will be next month? And we asked questions about specific variants, like the percentage of B117, which was certainly of interest in March 2021. So we asked these people, we didn't ask them just cases and deaths. We asked a variety of questions. And there are summary reports on GitHub that I'm happy to share with you that summarize all those results. Okay, you get these predictions from people, you get these predictions from models, but you need to combine them, and that's not so straightforward. So what do? Well, the data looks like this. In the top panel, you have each model. I'm defining a model as either a computational model or a human judgment model. You have each of the different targets, and you have quantile estimates for all of them. That's the data. The model is a convex combination of those quantiles. So if you have 20 computational models and 10 human judgment models, you're going to take essentially a weighted average of each of those quantiles, 7 for cases, 23 for deaths. But the question is, how should you weight them? So we chose this ensemble algorithm we chose, we're calling it like a performance-based ensemble algorithm, is we're going to look at a scoring of all the human judgment models. So we scored all human judgment models, we scored all computational models using the weighted interval score. Lower weighted interval scores are better, higher ones are worse. We looked at the average weighted interval score for each of the different possible combination of weighted vectors, and we said the one that minimizes that, that's the one we want. All right, so we're going to just plug it in and find the weighting vector that gives us the smallest average WIS score over past surveys. Seems straightforward. I thought like, oh, I'll just use Newton-Raphson and like we're done here, right? So the number of models you have are 40 to 50 computational models and 60 to 100 human judgment models. And so your weight vector is about 150. And Newton-Raphson doesn't do well in high dimensional spaces like that. Right? And so we had to come up with something different. And the algorithm we chose to optimize these weights is called differential evolution. It's a searching algorithm. So shown here, you have some space and some potential population of solutions, and they are combined randomly. It's called like mutation and drift. It has like these evolutionary themes to them to build a new solution. And it does this iteratively over time and time and time. And it's really robust in high dimensional situations. And it worked quite well for finding weights that resulted in small average WIS scores. So the data is quantiles. We're going to just take a weighted average of them, and we're going to use this thing called differential evolution to do so. Seems easy. Another problem. Humans are humans. We are unreliable. We forget, right? We have 1,000,002 different things calling our attention every single day. And maybe going to a prediction platform and submitting a forecast is not on the top of that plate, right? And so what I've shown here is the 6 surveys, incident cases, deaths, incident cases, deaths, incident cases, deaths predictions for the COVID-19 forecast hub. Human judgment models submitted by that deadline, and human judgment model just submitted in, by the end of the survey. Blue squares are they made a prediction. Yellow are they did not. And you see that computational models did very well, right? These are automated. And if you look at what the number of proportion, I guess, of human judgment models submitted by this deadline, they didn't do as well. And so you have this massive missing forecast issue. We thought of 2 strategies. We're calling one the defer to crowd strategy, one spotty memory. These we're going to say are different human judgment models, 3 of them over time. X's means they made a prediction. Blank means they did not make a prediction. For the defer to the crowd approach, we're going to include forecasters if you've ever made a prediction. So if you made a prediction in survey 1 and then survey 5, you're still included in our ensemble algorithm. We're going to impute those forecasts target by target, quantile by quantile. So in some sense, it's like built-in regularization, right? If you do mean imputation over the quantiles, you will have several mean quantiles because several people are missing forecasts. A second approach, which I think is maybe more realistic, is a spotty memory approach. You're only going to include those who made forecasts for that survey. And you're going to impute previous predictions that they've missed. And you're going to do that to support estimating weights, because you cannot estimate weights with missing scores or missing predictions. You'll get the answer you will get is NaN otherwise. So we took these two potential strategies to impute all of the missing forecasts from human judgment. Okay, results time. Look at these 6 surveys. Let's look at them for incident cases in the top panel, incident deaths in the bottom panel. Let's look at paired WIS scores for this chimeric ensemble versus an ensemble of computational models only. This black dashed line is 0. That's when WIS score is the same. We looked at all of the different approaches. So defer to the crowd in this dark solid bar, a spotty memory in this dashed bar, and several different ways to impute those quantiles: mean, median, Bayesian-rich regression, decision tree, extended tree regression. The dot is the mean WIS score, paired WIS score. The 2 bars are 1 standard deviation. The whole bar is 2 standard deviations. If you're below that line, chimeric forecasts have better accuracy or better performance. If you're above it, computational models win. For cases, in general, a chimeric forecast had improved predictive performance compared to a computational model only. And the opposite is true of deaths. So human judgment was able to help or improve predictive performance for cases. And if you start adding everybody in for deaths, you will do worse compared to computational models only. It's worth looking at this whole performance weighting algorithm versus equal weighting, because it's a common theme that equal weighting just wins, and that it's very difficult to try and choose differential weights. And we see the same thing here. So I plotted paired WIS scores for those 6 surveys for this performance weighting versus equally weighting. 0 would mean they have the same score. Below the line would mean performance weighting wins. Above the line would mean equal weighting wins. For cases and for deaths. For cases, it doesn't, it makes no difference. This big algorithm, all these things, computing all these differential weights. Equal weighting does about the same. Common theme: it's difficult to predict someone's performance in the future based on their performance in the past. This has been a recurrent theme in not just my work, in many other people's work in the past. It did slightly better for deaths, but still not enough to convince me that performance weighting knocks it out of the park. These sorts of algorithms that try to differentially weight people based on their past performance. Because another thing about people is slightly unpredictable.
Hi, this is Jennifer. Sorry, I think my question wasn't very clear. I was asking, you said when you included more people, more observations, I think that's what you said, that the predictions for deaths were worse.
Yes, that's true.
There was a human directional bias. Were people more likely to overestimate or underestimate?
Oh, boy, I don't know. I didn't look at that.
Okay, thank you.
That's a good question. I'm going to now. Thank you. I don't know if they always over or underestimated, or if there was a bias there. I'm sorry, I don't have that answer for you.
So Tom, I have a question as well. On the point in the last slide, or maybe it was the slide before, did you look at this for the not chimeric model, or sorry, I guess it's the next slide, when you're comparing performance-based versus equal weighting? Do computation, do the results look the same whether you're looking at only computational models and only expert predictions versus looking at the chimeric model? I guess part of what I'm wondering is well, these forecasters are chosen because they're supposed to be good. So maybe the idea is that well, if you're good at forecasting infectious diseases as a person 1 week, you should be good later on or something like that. But I guess a computational model, I could see how there's just a lot of noise and fluctuations that could happen. But did you look at that?
I didn't look at it for this project, but in the past, we tried to do this differential weighting just for humans and found that it just doesn't improve anything. It's you get roughly the same scores. And this, I feel like every person that enters this field is I'm going to be the one that figures out how to weight them to get improved scores. There's this history of papers that are the papers here's this new way that we're going to weight them. It doesn't do any better than equally weighting. there's like a litany of these types of papers. So we did that previously, and then in previous work in influenza, it was just computational models. We built an ensemble algorithm that's supposed to improve performance, and it did, but only slightly. So I think in general, performance weighting is very difficult. Not necessarily only in this chimeric realm, but I think just computational models and just human judgment is difficult to do, especially human judgment. We found in those past two experiments that if you just look at someone's current performance and their future performance, there's almost no correlation.
I have then another question also. So it's known that when you try to, when you combine what's it called, like opinions of different experts, one problem that there is if the experts are correlated. So if the experts all rely on the same data to make their decisions, which could hurt in both cases, right? Both for mean and for trying to do weighted average. Is there like ways to try to deal with that?
Yeah, I think the traditional way is to model the weights as some sort of transformed multivariate normal with a correlation, and you estimate a covariance matrix between all the different folks. I think that's the traditional approach. That's by Winkler and, oh, I can't remember the other person's name. I can send you the paper if you're interested, though. There are traditional approaches to trying to model the correlation between several different people. And the most traditional one is to model their performance as a multivariate normal with a covariance matrix.
Okay, thank you. Yeah, they sent me a link.
Yeah, I will, for sure. That's a cool paper. So that previous stuff, we added in all computational models on all people, but maybe there's some sort of mixture of people and computational models that performs better. And so to look at that, we looked across all the 6 surveys, and we randomly sampled from 0 to 20 computational models and from 0 to 20 human judgment models. Equally weighting only. We did this sampling 150 times without replacement, and we looked at the average WOS score for each of these different possible combinations for cases and for deaths. At one point, I broke the cluster computer. Someone had to reboot it for this next couple of slides. And what do we find is for incident cases, so the mean WS score here, the dark blue or purple colors are better, and the lighter colors like green, yellow are worse. We find that for cases, a high number of computational models and a high number of human judgment models does better. You need a lot of both. That's not the case for incident deaths. You need a lot of computational models, and you don't need 0 human judgment. It actually does a little bit better if there's like 2, 3, 4 human judgment models in the mix. You get slightly better WIS scores than if you had no human judgment. So although human judgment, adding in everybody, does quite poorly for incident deaths, little human judgment helps. It's not fair to look at this averaged overall surveys, right? And so I didn't include in this presentation, but I do have them survey by survey, and there is variability in this, but it's roughly this theme. Now you can look, instead of a mixture of computational models and human judgment, why don't I do this? I'm going to include all computational models for sure, and I'm going to incrementally add 5 people, 10 people, 15 people, 20 people. And I'm going to do this again at random, sampling 500 without 50 without replacement. Several different times. I'm going to look on the horizontal axis is the number of human judgment people included. On the vertical is the average WIS score over these sampled replacements. I just plotted a ton of different imputation techniques, the complete case, the decision tree cases. And I wanted to see if you incrementally add people to an ensemble where you include all of the computational models for sure, what happens? Is the same theme come out? And the same theme sort of comes out. For incident cases on the top, as you incrementally add people, you improve your WIS score. You improve predictive performance. as you incrementally add people, you do worse for deaths. And so having some human judgment is good for deaths. You see that the WI score here for 5 is low, but as you add 10, as you add 15, as you add 20 human judgment models, it does incrementally worse for predictions of death. So that same theme is kind of variable over the different surveys. I have survey 2, 3, 4 was a goofy one, so I excluded it for now, 5 and 6. And there's variability there, but overall, that is roughly the theme. That's not only the theme in this work, that's the theme in work from friends Nikos Bassi and Sebastian Funk, who did this also, and they found that people are good at cases, not as good at deaths. Now, okay, so we did this work. What are the conclusions? What are the future directions? What can we do? This was an exploratory analysis. This was not meant to be definitive at all, certainly not with 6 surveys, right? And 12 questions asked. But the 3 conclusions or 3 takeaways that I had was that human judgment can support predictions of incident cases and deaths. It can, there's something here. Missing forecasts are a huge methodological challenge to address if you want to do this sort of chimeric forecasting. And performance weighting, at least for this experiment, is not supported as more accurate than equally weighting. In the future, some sort of mechanistic model that accounts for missing forecasts and weights simultaneously might be better. Maybe a model that determines ahead of time whether or not you should enlist humans to help you forecast this target. Or you could imagine maybe you're asking some question, but humans have a finite amount of time and you don't want to force them to make predictions for something that will not be helpful or benefit the analysis. There's implementation strategies to reduce the number of missing forecasts in general. How do we motivate people or remind them to make forecasts? I don't know. There's a human psychology angle here. One thought was that the reason they're good at predicting cases and the reason they're doing worse than computation models at predicting deaths is because they were not using the time series of cases to help them predict the time series for deaths. And so you might ask in a controlled experiment whether humans can use information from one time series to predict another, which is this field called multi-Q probability theory. How do we use probabilistic information to help us make predictions? And then finally, there's a crowdsourcing experiment that we're launching today. Let's see if I can find the link for you and give you a, yep, here we go. So tournament starting today, anyone's welcome to sign up. It's going to follow the flu site challenge for confirmed influenza hospitalizations that the CDC is running. We're going to ask about 6 key states. And just as an example, let's look at Wyoming. We will ask every 2 weeks, what will be the total number of confirmed hospitalizations due to influenza in Wyoming for these 2 dates. And again, you can go down here and shift and scale and make your own prediction and submit it. And that will be run from now until somewhere in May. Oh, and you can also add comments like, I've used this information otherwise. Just want to acknowledge the CDC, the Midas for support and funding, Matadkos and Good Judgment, my research lab. We're all amazing folks. And I also want to say thank you and questions and thank you to these creatures in this slide too.